Okay, so thanks everyone for waiting. And
so real quick.
yeah.
Sorry about the delay.
Yeah,
we
yeah.
had Alberto with Atlassian. I don't know if you saw me misintroduce him earlier, but if
Alberto.
So I could put you from WebRTC Ventures, but I think we'll not do that. So George Politis is going to share with us some of his work with Atlassian and the University of Strasbourg on optimizing the infrastructure, costs, and call quality in WebRTC.
Yeah. So thanks everybody for being here. Good morning. My name is George. I'm a PhD student at the University of Strasbourg in France, and a senior software engineer at Atlassian in a Meet team, where we build Jitsi Meet and the meet.jit.si service. Yeah, today I'm going to be talking about how to minimize the infrastructure costs and maximize your code, the quality of the code that you have in your service. So before we begin, before we dive into the details, I would like to give a few details about our stack and the service that we are running, our cloud service, and some representative numbers of our service. So here we can see here is the Jitsi Meet stack. We have it's not all of the components, just the main components that we have. We have a signaling server on the server side and the SFU. And on the client side, we have two applications, a web application that is built on the WebRTC JavaScript API that was presented by Bernard Boba on Monday. And we also have a mobile application that runs on the mobile, and it's built on React Native for code reuse, so it runs on iOS devices and Android devices, and it's built on React Native with React Native WebRTC. For the signaling path, we're using XMPP provided by Prosody, which is an XMPP server written in Lua, and for the media path we have, we're using UDP, DTLS, and SRTP as is mandated by the WebRTC standard. So here is what Jitsi Meet looks like. This is what you would get if you join our cloud meet.jit.si URL, or if you install it on your own VPS. So here we see Yana, which is on stage and is being received in HD resolution, 720p at 30 fps, and on the horizontal thumbnails bar we have a bunch of our colleagues. So you can see Pavel, Boris, and Christo. They're being received in 180p at 7.5 fps quality. This is actually a screenshot from our daily stand-ups. We have multiple layouts. And each layout, and depending on the layout, the appropriate quality is being received by the receiver. We have a Brady Bunch, a newly committed Brady Bunch layout where you have all the participants in equal rectangles appear on your desktop, and they're all being received in 360p resolution instead of 720p. So we really do take the viewport into account. We have many other features that are not really relevant for this presentation. We have speaker stats, desktop sharing, transcriptions using the Google transcription API, recordings to Dropbox, telephony support, and other stuff. So a few words about our infrastructure. The projects that I just presented are all open source, so you are free to install them on your own VPS, on your own infrastructure. What is not open source is the way we scale and build our infrastructure. So we scale horizontally using sharding. We deploy on multiple AWS regions. We have deployments in Frankfurt, Ireland, North Virginia, Oregon. We deploy all over the world, and Australia. So each shard contains all the necessary components to hold several conferences. We have the signaling components. We have an auto-scaling group of SFUs, so in case lots of traffic is driven to that specific shard, we auto-scale the SFUs in order to cope with the extra traffic. And we also, each region outside of the shards has an auto-scaling group of turn servers in order to support peer-to-peer connections that cannot connect directly, but they need a turn server to connect. Our SFUs and our turn servers are built on C4X larges. Oh yeah, okay. I was thinking that my presentation is not fully. You cannot fully see my presentation, but you can actually see it. So it's dedicated C4X larges. We use dedicated machines because we've had problems with shared hosting in the past. A few numbers about our service. So this past month in September, we no. I am accepting the risk. Yeah, I'm a risky person. So yeah, we had about 91,000 conferences. The average conference duration was 38 minutes, and we had a little bit more, 3 to 4 participants on average for every call that we have. And these amounts for 3.5 conferencing minutes, and our average RTT time is 300 milliseconds. So minimize cost and maximize call quality. In terms of minimizing cost, this really translates to infrastructure costs. You want to minimize the data transfer. You want to minimize the virtual machine operational costs. So that's what you're doing on the infrastructure side. And in order to maximize the call quality, you want to deliver the most bits within the limit set by the network and the CPU. For example, and for that you need a good congestion control algorithm in order to be able to detect as close as possible the real network link capacity. And you want to be careful now that you have more and more mobile devices. You want to be careful not to send a lot of amount of data and risk draining the battery too fast, or risk having a choppy video experience because the decoder chokes and it starts to drop frames. So a lot depends on the architecture. A lot of your options depend on the architecture that you choose. In the past, video conferencing providers have been using MCUs. These have several. This is a necessary evil. Sometimes you need to transcode media streams in order to support legacy devices. But if you want to build something for the future, you will go with a selective forwarding unit, which is much lighter than MCUs. And instead of transcoding media packets, they route media packets. So it's not as simple as an IP router, and we will see exactly how it's done. But it's a way to go if you want to build a scalable infrastructure and reduce the costs. So the best way to introduce an SFU is through the example of simulcast. Simulcast is a hot topic right now, both in the W3C and in the ITF. There's a lot of people working on standardizing how to control it and how to configure it. Right now, it's sort of hard-coded in the WebRTC media engine. You don't have a lot of flexibility in the things that you can do, but that gives time to vendors to adjust their code and incorporate simulcast slowly by slowly. And the way it works is a specific sender streams multiple versions, multiple streams of the video stream that it's sharing. So in this specific example, we have senders sharing their video feed in 3 resolutions, 720p, 360p, and 180p at 30 fps. And the SFU decides, based on the viewport and the video and the layout of the receiver, which resolution to forward for each sender. So the receiver only gets what it needs to display in the specific viewport and video layout that he has. This, along without any congestion control, without talking about the congestion control, alone simulcast can greatly help and reduce the ingress bitrate at a specific participant. And this has, of course, you conserve bandwidth, and it also has an impact on user experience because decoding and CPU resources are proportional to the ingress bitrate that you're processing. So the less ingress bitrate you're processing, the more fluid experience you will have in your call. Just an example: if you are in a 10-way call, you are receiving with simulcast. You're going to receive 3.7 megabits per second, and if you don't have simulcast, you're going to receive many times that amount, and it's 22.5 megabits per second. So it really helps even without doing anything fancy just by doing simulcast. And this is on the receivers. From the receiver's perspective, the savings on the server are much greater because the egress bitrate on the server grows quadratically with a number of participants in a specific call. So, for example, if you have simulcast in order to support a 10-way call, you would need about 37 megabits per second, whereas if you don't have simulcast, you would need 220 megabits per second. And with 4 10-way calls, basically you exhaust 1 gigabit, which is pretty bad. So simulcast really helps. Now, the close cousin of simulcast is SVC. The idea is the same, but instead of actually sending 3 streams, you send 3 streams with substreams embedded in these streams. So the 720p stream can be broken down into 30 frames per second, 15 frames per second, and 7.5 frames per second. So the SFU has more choices on how to allocate and how to distribute these streams to a specific receiver. So in this specific example, we can see that the receiver is getting 30 frames per second, 720p for the on-stage participant, and just 180p at 7.5 frames per second for everybody else that sits on the thumbnails. Yeah. So we also have other techniques other than simulcast. We have last 10. So the way this works is the bridge doesn't do any decoding of the audio stream. So it needs other means to perform dominant speaker identification. So along with the media packets, there is an RTP header extension that gets injected into the media packets, and we can extract audio level information from the RTP packets without doing any decoding. And based on the audio level information, we have an algorithm in the bridge that performs dominant speaker identification. And based on that, by continuously doing dominant speaker identification, we can build a list of active speakers, and that list changes dynamically. And with last 10, for example, set to 2, we can forward to a specific participant just the last 2 active speakers instead of everybody. And this is beneficial, for example, when you're on mobile and you don't have a lot of real estate, real estate. I mean, you have a very small screen. You don't want to forward everybody. You just want to forward 2, 3 last active speakers. And in some cases, you just want to forward the on-stage participant. But that's a setting. That's a last n setting, setting the n equal to 1. So I briefly mentioned about congestion control before. Last n and simulcast alone, without doing any congestion control and without complicating things, can help. But in order to be able to really minimize costs and deliver the best possible user experience, it's not about cost, it's about delivering the best possible user experience. You have to take congestion control into account. So it's a very big topic. We're not going to, I mean, I just have one slide here to introduce the subject. Right now, we have implemented in the bridge the Google congestion control algorithm. The same thing is implemented in the browser as well. We have our own Java implementation. So it's not exactly the same, but it's close, very close to the browser implementation. It's a control feedback control algorithm. It has 2 parts: an AIMD, an additive increase, multiplicative decrease part that takes loss into account, and another part that takes the packet delay variation into account. And the idea is that while you have a positive packet delay variation, you're actually causing congestion and you need to back up on what you're sending. And when you have a negative packet delay variation, the queues are emptying and you can ramp back up. Of course, it's not as simple as that. You want to avoid situations with stale queues, but the principle is that. So the way this works is the sender is sending the media and the receiver is reporting back packet arrival times and packet loss. And the packet arrival times can be used in order to deduce the packet delay variation and feed that back to the algorithm and do its thing and produce a bandwidth estimate. So the techniques that I mentioned, last 10 and simulcast, If you add congestion control and bandwidth estimations on top of that, this is what you get. This is the overview of the SFU. So we have the senders. They're sending 9 qualities. They're sending audio level information, and you have a bitrate controller that takes the active speaker list. It takes the viewport information. It takes transport feedback to produce bandwidth estimates, and it computes a streaming configuration that's the most appropriate for the specific receiver. So in this example, the receiver is getting 720p resolution and 30 FIPS for the on-stage participant, and just one of the 2 senders at 180p resolution and 7.5 FIPS frames per second. So yeah, I have prepared a demo that will hopefully make all this much clearer if you're able to see the fine details on the screen. So here we are in a multi-party call. You can see all the participants here. I'm not sure if you can see the tiny letters, but we are streaming HD for the on-stage participant, everybody else. And we have the bits received per second is around 3 megabits per second. We activate the limitation. Well, it's more than 3 megabits per second. We activate the limitation, and the bits that we receive drops. That means that our SFU has reacted to this limitation. We can see that even though the bits that we received was reduced, we can still have acceptable quality. We reduced even further up to the point that we can only receive the on-stage participant, and by reducing even further, we cannot reduce anything but audio. So we go all the way back down to audio, and the bits that we receive is extremely low. If we remove all the limitations, we ramp back up, and we have a full conferencing experience. So the picture that I showed, yeah, and this is ramping up. It's 360p standard definition, and eventually it will go back up to 720p. And this is how, and it's 720p now. And this is how we adapt to bandwidth variations. Okay. All this is good if you're doing group calls, but in the study we have performed a measurement study, and we have found out that many more than half, actually 77.8% of the conferencing time spent on one-on-one calls. So you really want to optimize for that use case. And as we have shown yesterday, all these group calling features, simulcast, last N, adaptivity, and things like that, not only don't help, but they can hurt the performance of one-on-one calls. So you really want to be able to dynamically switch between the 2 use cases, group calls and peer-to-peer calls. We have implemented a mode. We have implemented this dynamic switching, and we have done a measurement study that showed that by activating this dynamic switching, we have reduced our bandwidth, our data transfer by 52%, combined data transfer, both egress and ingress, by 52%. The infrastructure pressure, we are now using 35 to 40% less memory, CPU, and much less system load. And also we have improved the user experience by improving the quality of service. We are now have one-on-one calls with this new mode of peer-to-peer for one-to-one calls. We have 20% to 30% shorter RTT, depending on the region, 20% shorter RTT in the US and 30% shorter RTT in Europe. And this mode this is the second and last demonstration that I have for you today. This shows this dynamic switching mode. I'm afraid you're not going to be able, no, maybe you will be able. So now we are in a one-on-one call, and we're in peer-to-peer mode. We are receiving 720p at 30 FIPS. Now a third participant joins. We enter in, oh no, I didn't want to close that. We're no longer in peer-to-peer mode. We have all these simulcast adaptivity features that I just explained, and so we switch dynamically to the group mode connection, and now we are back on one-on-one mode, and eventually we're going to go in peer-to-peer. So here we are in peer-to-peer, and it was seamless and transparent. So moving forward, this is something that we have only recently implemented, and it's called offstage sender stream suspension. Basically what happens is, if a participant is offstage for everybody else in the call, we are trying to suspend or reduce the bitrate that it's sending. So instead of sending 720p, and nobody receives 720p for that specific participant, we're going to cap the bitrate of the media. So we go down to 180p, for example, or we pause completely the stream if that participant has dropped and is not being forwarded at all. So this is this is very new. We don't have any data to share, but one can imagine that for example, in a 10-way call, we have seen before that the ingress bitrate is 3.7 megabits. With simulcast, the egress bitrate is about 3.2 megabits per second. So if you cap the egress bitrate at the sender down to, let's say, 150 kilobits per second, and you only forward his or hers 180p stream, and assuming that encoding and decoding have approximately the same cost, you're basically halving the pressure on the system pressure on the client's endpoint, which can greatly improve and improve the user experience for the specific user. So in the future, that's all great. We have many things planned for the future. We would like to experiment with hardware-accelerated H.264 simulcast. This will not only allow us to reduce the infrastructure costs, but it will also allow us to take advantage of hardware-accelerated H.264 and reduce the pressure on client machines. We have this problem in particular with mobiles because the battery drainage is very, it's a big problem right now. We would like to experiment with VP9 SBC. VP9 doesn't have the hardware acceleration that H.264 has, but it can, you don't have to do simulcast. You can embed all the streams, all the qualities inside a single media stream, so you can save some uploading, some egress bits on the participant side. We would like more granular sender stream suspension. For example, right now it's fixed with simulcast. You send 3 streams. However, we may want to disable, for example, you send 3 streams, high quality, high definition, standard definition, and low definition. You may want to disable the standard definition, for example. You want to have some more granular control over this, but there is some standardization work to be done there, and this is on pause. We want to optimize that data transfer when using cascading bridges. This is another new feature that we have in our projects. We now support cascading bridges, but you don't want to forward all the media between all the bridges that you have. You really want to do something smart there and reduce because you end up in a mesh situation, but with the bridges. So you want to be more smarter there and not transfer everything to everybody. We also plan congestion control improvements. We want to have more aggressive bandwidth probing. We want to ramp up faster when there is a network event and the bandwidth estimation drops. And lately we have seen that actually it was 2 weeks ago that the WebRTC adapted BBR has been committed and it's ready. We don't know when they're going to release that and when they're going to activate it, but this is definitely something we want to be looking into. And that's my presentation. Thank you very much and please, any questions or answers?
Thank you, George.
Thank you.